Hi everyone. So we're going to continue on with Lewis structures and talk about drawing polyatomic ions, Lewis structures for polyatomic ions, and then resonance structures. Now, we have to draw these also in homework, and I had said on an earlier video that I would take a video of my screen while I'm entering them into WebAssign. I actually found that I had done that a couple of years ago because the computer didn't work in the classroom or whatever. And so I already have a video, and it's going to be for the ICL5 example and the ozone example that we're going to do today. So you can find those, that was from the previous one, and the ozone we're doing in this content video. So there you can enter those into web. So it's an assignment on WebAssign, a free homework assignment where you just enter what we did in class, so to speak. And linked in the instructions is a video that I did showing how to do that on WebAssign. Okay. And so I don't think the Marvin sketch is going to be hard for you to figure out. It usually isn't. But I wanted you to have that in case you ran into any trouble entering. And of course, post any questions if you have trouble entering them into the Marvin sketch, and I'll help you out. So let's start with the example of how to enter, how to write a Lewis structure for a polyatomic ion. Okay, so we've got the chlorate anion, ClO3 minus, and let's just write the Lewis structure for it. So go ahead and do that, and then pause the video and then come back. Okay, so first step is count the total number of valence electrons. So chlorine is in group 7, so it's got 7. Oxygen, there's 3 oxygens. I always put that in parentheses so it doesn't look like I'm writing 30. 3 oxygens, group 6, so there's 6 electrons in each, 6 valence electrons. And then what about this -1 charge? How would you do that? Well, the -1 charge means this molecule, which is an ion, so a polyatomic ion, it's covalently bonded, but it has a -1 charge. That's an extra electron, so one more electron. All right, so add them up. 3 times 6 is 18, plus 8. I hope I get this right. How embarrassing would that be? 26 electrons, or 13 pairs. Okay, so in writing the Lewis structure then, we're just going to stick the first atom in the middle, and then we'll connect oxygens to it with single bonds. And then now we'll just put the rest of the electron pairs around the structure and then move around as we have to follow the octet rule. So we've got 3 pairs. I'm just going to go ahead and fill in the octets for the oxygen until we get to 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we've filled the octets on oxygen, but we still have another pair of electrons. So it looks like that one's going to have to go on the chlorine. I'll put those with dots so they stick out a little more. All right, so there we go, right? This is a good Lewis structure if we're going to follow the octet rule. So this has filled octets on all atoms. And you could be, in the homework or on the test, wherever, you could be asked, write the Lewis structure that follows the octet rule. And this would be it. But we're also going to have to check formal charges. Before I do that, for polyatomic ions, there's one other thing we have to do. And so on paper or in the book, what we're going to do is we're going to put square brackets around the structure. And then it has a -1 charge, so we'll put that minus. If it's -2, you put -2, so on. And so the tradition has been that on paper, or that's how it will be in the book, you just indicate the charge. You don't have to indicate where in this polyatomic ion does that charge reside. It's just on the whole thing, right? We don't make the distinction. And so you put square brackets and then the charge out there. But on a computer drawing program, we're going to enter formal charges and not use the square brackets. So we'll talk about that later. Anyway, so this is a good structure for following the octet rule, but let's check formal charges. We better do that to see if it is a good structure. All right, I'm going to write those in red. So remember, the way to get formal charges is how many valence electrons would the atom, the element, normally have if it's a neutral atom. So oxygen's in group 6, it's supposed to have 6. And then how many does it own? How many are on it in the structure? So the lone pairs count completely on that atom, and then the bonding pairs count half. So when we count it, we'll count the lone pairs like this: 2, 4, 6, and then the bonding pair just counts as 1. So it's 2, 4, 6, 7. So oxygen is supposed to have 6. It has 7, so that has a -1 formal charge. And if you look, all the oxygens are the same, right? They all have 3 lone pairs and a bonding pair. And then the chlorine is in group 7. It's supposed to have 7 valence electrons. It has 2 for the lone pair, 3, 4, 5. Supposed to have 7, but it has 5. It's missing 2. So missing 2 means it's a +2 charge. And those are the formal charges. The other thing to notice, the formal charges have to add up to the charge on the ion. So -3 + 2 is the -1 charge on the whole thing. But what the formal charges tell us in this case is that's not a great Lewis structure for this ion, this polyatomic ion, because the charges are really, split up. +2 on the, chlorine, that's pretty electronegative compared to, both oxygen and chlorine are close to fluorine, right? But it's not evenly distributed. This is not good in terms of formal charges. We want to minimize those. So let's draw a structure that minimizes formal charges. All right. So draw the structure that minimizes formal charges. That was not a mouse scurrying across my desk. That was a sticky note that decided to jump for freedom. Anyway, so when we look at this structure, what's a way to get those formal charges down? Well, oxygen's got too many electrons on it, right? So what if we take this lone pair and share it into a bonding pair, exceed the octet rule on chlorine, because all these are following the octet rule. And when we do that, it's going to decrease those formal charges. So let's draw that one. So I'll just redraw it with a double bond between that oxygen and the chlorine, and everything else will stay the same. And now there's only 2 lone pairs on that oxygen. So do you see what I did there? I just took this lone pair, moved it in to make a double bond there. Everything else is the same, right? And that's a good structure, but has it minimized the formal charges? Well, let's take a look and see what it is. Assign formal charges to this then, and pause the video and come back, or at least try and stay ahead of me, right, when we do it. So these oxygens haven't changed, so they're still -1, right? But now this oxygen should have 6. It has 2, 4, 5, 6. So now that's a 0. What about the chlorine? It's supposed to have 7. It's got 2, 3, 4, 5, 6. So now it's down to a +1. So we've improved the situation. Right? We've improved the situation a little bit. But we can do even more, can't we? We could take one of these other oxygens and have it share into a bonding pair. So let's do that as well. So I've got my chlorine in the middle, and I'll double bond to both oxygens on the sides. Leave my lone pair there. This oxygen hasn't changed. Okay. And now this structure, if you go through and do it, has 0 formal charge on this oxygen, 0 formal charge on the chlorine, and 0 formal charge on this oxygen. The oxygens are the same as we already did that. Let's do the chlorine. It's supposed to have 7, right? It's got 2 from the lone pair, 3, 4, 5, 6, 7. It's supposed to have 7. It has 7. Formal charge is 0. And so this is the structure that minimizes formal charges. What's the best structure? Well, we don't have a best structure. I mean, this is the best Lewis structure we can draw. It minimizes formal charges. Chlorine is capable of expanding its octet, so it can do that. But when we look at this experimentally, it turns out, you know, if this structure really was the polyatomic ion, then we would expect to see a single bond and 2 double bonds, right? But if you look at it, we find out that the bond lengths are all the same. It's a really important point here. And so there aren't 2 different kinds of chlorine-oxygen bonds in it. Remember, the Lewis structure is not the structure of the molecule or polyatomic ion. And in fact, when you look at that, the chlorine to oxygen bond, I even went and looked this up, has a bond length of 0.149 nanometers, and they're all 3 the same. And it's somewhere intermediate between a single bond, a normal single bond, and a double bond. And that brings us to that's our segue to the next topic, which is resonance structures. Okay. I guess, I forgot again. So I do want to say on WebAssign how to enter this. So let's do that. And again, I'm going to have video in the instructions on entering these. But I want to stress this because it usually causes some confusion, and I don't want you to be frustrated. So when we draw this structure on paper, so I'm redrawing the same structure. You shouldn't have to redraw it. When we draw that structure on paper, traditionally we'll draw it with square brackets and the charge out there, and that's how it would be represented. On WebAssign, which uses something called Marvin Sketch. So there's a lot of these different computer drawing programs for drawing Lewis structures and molecular structures on computers. And they're not just drawing, it's not a sketch like just drawing things. It actually has the chemistry built into it. And so it knows what a single bond is, it knows what a double bond is, it knows what formal charges are, and it does calculations. You can even do 3D things, and it's all kinds of really cool stuff. And so it's chemically intelligent software that's doing this. And they're not, anyway, I don't need to go and explain a whole bunch of what it's doing. But when you're drawing on any program, we won't include the square brackets like we would on when we're just drawing it on paper or in a diagram in a book. So we won't include the square brackets. So you can't add, I guess what I'm saying is you can't add anything extra into that Marvin sketch. And the charge then, you know, where normally we haven't indicated where the charge resides in the polyatomic ion, on a chemical drawing software, we have to do that. And so for a polyatomic ion, you must include formal charges. And I will just say, so for the homework, the textbook homework, they should say in the question whether or not you need, you know, if it's a neutral molecule, whether or not they want you to include formal charges or not. And so just look at the instructions for each question, because you can code it either way. I've coded some questions in there myself that are part of the homework. And so if it says include formal charges, you have to include them. Sometimes you do, sometimes you don't. Just depends on how the problem's set up. All right. Okay. And then now my segue to resonance structures. I almost forgot to tell you about the drawing on the Marvin sketch. All right, so we're going to draw ozone. Where am I at time? Oh my goodness, going slow. So ozone, 3 oxygen atoms. That's 6 electrons because it's in group 6. So we have a total of 18 electrons, which is 9 pairs. And you should pause the video and draw this Lewis structure yourself. Okay. Now we'll connect it with single bonds. They're in a straight line. We're not going to have a triangle for other reasons that we'll learn about when we do geometries. It's really hard to put things into a ring like that if there's so few of them, like a triangle. So ozone would have 3 oxygens connected like this. And now we'll just put the other pairs of electrons around the molecule, right? We don't know where they go yet. We're just going to try and follow the octet rule. In fact, oxygen has to follow the octet rule. So let's just stick them on there. 9 pairs. We've used 2, 3, 4, 5, 6, 7, 8, 9. I tend to put them towards the outside of the molecule just because I think it's easier in moving them around that way. But I could have started with 1 here and less there. That would have worked fine too. All right, so I think we have the right number of valence electrons shown. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now we just check to see if we followed the octet rule. So the oxygen on the left here has 2, 4, 6, 8. So does the one on the right, but the one in the middle just has 6. It doesn't have enough. So what we're going to have to do is we're going to have to share one of these lone pairs into a double bond. So that will give us a double bond here and look like that. Now, does that look like a good Lewis structure to us? Well, have we followed the octet rule? Oxygen here has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. Oxygen on the right, 2, 4, 6, 8. Fantastic. It has the right number of valence electrons. We followed the octet rule. And since we have to follow the octet rule, formal charges, what are we going to do, right? But let's go ahead and assign formal charges anyway. So I'll just write them. I guess I can write them right on there with red ink again. So oxygen's in group 6. It's supposed to have 6 valence electrons. What's the formal charge on this oxygen on the left? It's supposed to have 6. It has 2, 4, 5, 6. That's a formal charge of 0. All right. Oxygen in the middle, supposed to have 6. It has 2 from the lone pair, 3, 4, 5. So it's missing an electron, right? So that's going to be a +1. And then on the right, it has an extra electron, doesn't it? Because it's 2, 4, 6, 7. So that's a -1 formal charge. And again, the formal charges have to add up to the charge on the molecule or polyatomic ion. So ozone's a neutral molecule, no charge. So -1 and +1 adds up to 0. So we're good. All right, but just like the previous one where we said there weren't different chlorine-oxygen bonds in that polyatomic ion, let's do the experiment. Let's look at this molecule. And when we measure the bond lengths, we find that the oxygen to oxygen bond length shows only one type of bond. So we don't have a single bond and a double bond. We have something else. And so we're going to draw what are called resonance structures for this. And so I'm just going to redraw that Lewis structure down here. So, well, you can see it. Hopefully you wrote it down. So I'm just going to redraw it. Oxygen, double bonded to oxygen, single bonded to oxygen, and then I'll put the pairs around it. Okay. Make sure it's focused. Hopefully you can see that pretty well. And then I could have, instead of making the double bond between on the left, that was just, working left to right. If I were one who had a language where we read from right to left, maybe I would have started here and done it on this side. And that would have been equally valid, right? And so we can think of another Lewis structure coming that other way. Well, let's pretend like we can freeze these oxygen atoms in place and put little tags on them. A 1, a 2, and a 3. Okay? And now let's redraw it the other way, where we leave the oxygen on the left. Oopsie, I meant to do that in black, so now I'll label them in black. Doesn't matter. And then this one has the double bond going to this side, right? Okay, so you see these two equivalent structures. These are equally good Lewis structures. In this one, we made the double bond between the left, between oxygen atom 1 and 2. In this one, we did it between 2 and 3. And how do we decide which Lewis structure is the best Lewis structure? Well, they're equally good, right? And we know that neither one of them represents the real molecule, because when we did the experiment on the molecule, we found that we didn't have a single bond and a double bond. There's only one kind of oxygen-oxygen bond, and it's somewhere intermediate. Now, traditionally, so these are called resonance structures. I guess you probably guessed that, since that was the title of the topic, right? These are called resonance structures. And it's traditional in a book or on paper to put an arrow back and forth between these. I think that that's actually tends to cause some confusion. So I want to stress a couple of things here. It is not the case that it's 1 second or 1 nanosecond it's a single bond here, and the next it's a double bond here. It's not, this arrow kind of misleads us and makes us, or at least it did me when I was learning this stuff, makes us think it's flipping back and forth between those. And the same thing with the term resonance structures, right? Like a string vibrating, resonating. It is not flipping back and forth between these two structures. So let's put a, this is the most, I guess I'll just tell the story. I normally in class I would tell boring stories. So every year for the last few years, I've told the class that I want everyone in the class to get this question right on the test, because I put it on every single test. And so this concept that it's not flipping back and forth between those, that the real structure is an average of that. Okay, so the real molecule is an average of the resonance structures, all the contributing resonance structures. It's not flipping back and forth between them. I'm going to write that here too. And that's really confusing to a lot of people. And I've been trying for the last few years, because I think it's an important concept when you go into organic chemistry and just kind of understanding it. And I think it's really cool, right? So things that I think are cool are going to tend to be things that get stressed more. But so make sure that you say this with your bedtime prayers, and post a question if you don't really understand what I'm trying to get across here. But the point is the Lewis structure is not the molecule, right? We can't draw a Lewis structure. We can't draw one Lewis structure that represents this molecule. It's really an average of these two, not that these two both exist and it flips back and forth between them. And so you could think about drawing something like this, and this is the actual showing the shape a little bit that we won't talk about till later, why it ends up being that shape based on the orbitals on it. But I can't show the lone pairs on these outside like oxygens because it won't make sense. But so this single bond there between each oxygen, there's also then an orbital here that actually spans across all three oxygens and has 2 electrons in it. And those electrons are what we call delocalized. Delocalized pair of electrons. And it's actually then a bond that goes all the way across all three. So a Lewis structure doesn't really do it justice in this case. But if you wanted to think of a static Lewis structure that represents the actual bonding, this is a little closer to it. There's 6 electrons in this. Well, no, I don't want to say it like that. There's 2 electrons in this pi. Well, I can't talk about pi bonds either. Anyway, so the idea that when you have resonance structures, you're going to have delocalized electrons, right? And that we can't draw just one Lewis structure to give it. Then the other thing is, what would be the bond order for the oxygen to oxygen bonds? What would be the bond order? So if it's a single bond, the bond order is 1. If it's a double bond, the bond order is 2. What would be the bond order in this case? Does it make sense to you that it's 1.5? Okay. Well, think about that. Maybe read the section in the book if I haven't made it clear enough, or post questions to the discussion page about why that would be the case. But it's just halfway between 1 and 2, right? Halfway between a single bond and a double bond. And that's experimentally what we see, right? We only see one type of oxygen-oxygen bond. All right, thanks everyone.